Hello, today we're continuing with our series of GCSE physics revision. In the subject of waves, we're going to look specifically at refraction. Light travels at different speeds depending on what material it's travelling through. If you've got light in a vacuum, then its speed will be pretty much the equivalent of its speed in air, and that equals 3 × 10⁸ meters per second. But if you put through light through any other transparent medium, it has to be transparent, otherwise it won't flow through it, but anything else like glass or water or even jelly, then its speed will be less than 3 × 10⁸ meters per second. In other words, it always travels slower through any substance other than vacuum or air. And that means that when light goes from, let's say, air to water, it changes direction. It's travelling at 3 × 10⁸ meters per second in air, but it's travelling slower in water, and that causes it to change direction, and that we call refraction. There's a way of explaining this that may help, it may not. I'll tell you what it is and you can decide whether you find it very useful. This is a school playground. This is, as it were, the hard surface of the playground, very firm, and this is muddy grass. The point being that you can walk across a firm playground faster than you can walk across muddy grass, because that is going to slow you down. And we're going to take a series of children who are all lined up holding a long metal bar. So in other words, they have to stay in a straight line. It's vital, so they can all hold on to this bar, and they are all walking in this direction. So in other words, the bar is moving like this, and the whole thing is coming forwards. You get the idea. Now, all is fine until this group of children at this end get to the muddy grass. Once they get to the muddy grass, their progress is going to be a lot slower, because they're on the grass, than these children who are still on the firm playground. So what you'll find is that now these children don't get very far, but these children get further. And so consequently, the line starts to change. Again, these children won't get very far, these children will get further, so the line changes again. These children won't get very far because they're on the muddy, these are still on the playground, so the line changes again, until eventually all the children are on the muddy grass, and now they can continue to move at the same speed because they're all subject to the same muddy grass, but you'll notice that the whole thing has changed direction. And that is a very kind of simplistic way of considering how changing from one region where you can travel faster than in another region, there's a change of direction. So now let's go back to air, and this time we'll take glass. So here we're in air, here we're in glass. Here is a light ray which hits the surface. And once again, we're going to need a normal. The normal is always perpendicular to the surface. And we're going to have a refracted ray. So the ray has gone like this. This is the angle of incidence. This is the angle of refraction. We still use the letter R, but it's not reflection anymore. It is refraction. I can tell you that the speed of light in air, well, I've already told you that, is 3 × 10⁸ meters per second. The speed of light in glass is 2 × 10⁸ meters per second. It's only 2/3 of what it is in air. So there is quite a significant change in direction. I'm just going to remind you of something which I assume you've all done in your maths course, which is a right-angled triangle with an angle alpha. In that case, we call this line the opposite because it's opposite to alpha, this line the adjacent because it's adjacent to alpha, and this line the hypotenuse, and we say that the sine of the angle alpha is equal to the length of the opposite divided by the length of the hypotenuse. And that is, for any angle alpha, that fraction will always be the same. And the reason I told you that is because Snell's law says that if you take the sine of the angle of the incidence and the sine of the angle of refraction, then sine I divided by sine R is equal to the refractive index, which is called N, of the material. So for any material there will be one refractive index. For example, the refractive index of water is 1.33. The refractive index of glass is 1.5. The refractive index is always common for a particular substance. And sine I divided by sine R is the refractive index. It's also the case that the refractive index is simply equal to the speed of light in air divided by the speed of light in the material that we're talking about. So glass or water or jelly. So quick review, the refractive index is equal to the sine of the angle of incidence divided by the sine of the angle of refraction, but the refractive index is also equal to the speed of light in air divided by the speed of light in the material that you are, as it were, passing into. So here's an exam question. The refractive index of a particular material, not telling you what it is 2. What is the speed of light in that material? Well, it couldn't be simpler. We know that n is equal to the speed of light in air divided by the speed of light in the material. Rearrange that, you get that the speed of light in the material is equal to the speed of light in air divided by the refractive index. It's just manipulating that formula, and that's going to equal the speed of light in air is 3 times 10 to the 8th meters per second. N, you were told, was 2, so that's quite simply 1.5 times 10 to the 8 meters per second. So the speed of light in this material is half what it would have been in air. Now, you'll recall that we have so far been considering, if this is air and this is, let's say, water, we've been considering a light ray which comes in, we draw the normal, and then we have a light ray which is refracted. But it is entirely possible to do it the other way round. You can have the light starting in the water and then coming out into air, in which case the path is exactly the same. You'll notice that when the light was coming in, it bent towards the normal. When light is going out, it bends away from the normal. So when light is coming from a less dense medium to a more dense medium, from say air to water, it bends towards the normal. When light is going from a more dense medium, such as water, to a less dense medium, such as air, it bends away from the normal. And now, of course, the angles are reversed. This is now the angle of incidence, and this is now the angle of refraction. And in these circumstances, the sine of the angle of incidence divided by the sine of the angle of refraction is 1 over the refractive index, because we're now going the other way. So now we can think about how light goes through a glass window. We'll assume that there is air on either side of the window. Here is the glass, quite thick glass, but I draw this to make a point. Here comes a ray of light towards the glass. We construct our normal. Now, as it happens, some light gets reflected off of that glass surface. Not very much, but there will be some reflected light. And of course, as we've already learnt, the angle of incidence will equal the angle of reflection. We're not actually bothered about that too much. We're more concerned about the refracted light. There will be some light that will be refracted. And because it's going from a less dense medium, this is the air, this of course is glass, and then on the other side of the glass is air again. Because we're going from less dense to more dense, we bend towards the normal. But what happens when the light gets to the other side of the glass? Well, once again, we draw a normal, and once again there will be a tiny amount of reflection, but we're not really bothered about that. But again, the angle of incidence will equal the angle of reflection here too. But now we're going from a more dense medium, glass, to a less dense medium, air, and so the light is now going to bend away from the normal. And what we find is that it's travelling in the same direction, but slightly shifted. It was travelling a kind of northeast direction here, it's travelling in a northeast direction here, but it was slightly shifted by being, as it were, refracted or moved off course as it went through the glass window. Any transparent material will have a refractive index if light passes through it. And bear in mind that it always will go slower through the material than through air or vacuum. So here is air, and here is jelly. And here is my incident beam, and it will be refracted into the jelly. And I can tell you that the angle of incidence is 42 degrees. I can tell you that the angle of refraction is 35 degrees. I want to know what is the refractive index of jelly. Well, we know that the refractive index is equal to the sine of the angle of incidence divided by the sine of the angle of refraction, provided you're going from a less dense to a more dense medium. If you're going the other way round, then of course it's 1 over n, but we're all right here. So that's just going to be the sine of the angle of 42 degrees divided by the sine of the angle 35 degrees. For that you will need a calculator. The sine of 42 is 0.67. So n will equal 0.67 divided by the sine of 35, which is 0.57, and that is 1.18. So the refractive index of jelly is 1.18. Those watching in other parts of the world, particularly America, I think you called what we call jelly, I think you call jello or gelatin. I'm not entirely sure. Here's another exam question. This time we're going to have light travelling from water into air, so it's going from more dense to less dense, which means that it will bend away from the normal. So here is the angle of incidence, here's my light ray, and it will bend away so that the angle of refraction is greater. I can tell you that the angle of incidence is 17 degrees, and I can tell you that the refractive index of water is 1.33. What I want to know is, what is the angle of refraction? So now it's a case of using the formula where sine I over sine R is equal to 1 over n, because we're going from more dense to less dense, so it's 1 over the refractive index, which means that sine R is equal to n times sine I, by just manipulating this formula here. So sine R is equal to n, which is 1.33, times the sine of 17. The sine of 17 happens to be 0.29. So you've got that the sine of R, the sine of the angle of refraction, is 1.33 times 0.29, which is 0.386. And then you need what is called the arc sine of 0.386. In other words, what is the angle whose sine is 0.386? That's called an arc sine, and that is actually 23 degrees. So the angle of incidence, you'll recall, was 17 degrees. The angle of refraction is 23 degrees. It's moved away from the normal. Now I want to consider some special cases. Here is air. Here is glass. What happens if the incident ray is exactly perpendicular to the surface? Well, it may not surprise you to know that it will not be refracted. It just continues on its path. Why? Because sine I divided by sine R is equal to the refractive index. The incident angle is the angle between the incident ray and the normal, but that's 0 degrees because the incident ray is effectively travelling along the normal. So sine I will equal to 0 degrees, and that means that sine I is equal to n times sine r. Since n isn't 0, sine r must be 0, and that means that the angle of refraction is 0, which means that the refractive ray is perpendicular to the surface, so the whole thing is just perpendicular to the surface. Special case number 2 coming up. This only works when you're going from a more dense medium to a less dense medium. So I'm going to go from water into air. I need a normal. Here is my ray. That is the angle of incidence. So it's coming here. I've got a light source here coming through the water, and then as it gets to the air, it's refracted away from the normal. Now, if I increase the angle of incidence so that it's now larger, that will refract the light ray even further from the normal. And eventually I'll get to a point where it is coming along the surface of the water. And when that happens, the incident ray is called the critical angle. Sorry, the incident angle is called the critical angle. It's called the critical angle because it means that if you increase that angle of incidence, the light ray cannot be refracted anymore because it's already been refracted the maximum amount it can. All that will happen from that point on is that the light will be reflected back into the water. No light will ever emerge into the air. Once the angle of incidence exceeds the critical angle, no light goes out into the air. Remember, it only works when you're going from more dense to less dense. It can't work the other way round. And this, of course, is one of the reasons why you may not be able to see fishes in the water. Here you are on the bank. Here is the water. And here's a little fish. And you're looking at it, or you think you would be looking at it like this, but in fact, the light that's coming from the fish is striking the surface at an angle which is greater than the critical angle, and consequently all the light is reflected back into the water. Nothing comes out, so you can't see it. So if you're looking at this kind of angle, hoping to see fish in the water, you won't, because the light is totally reflected, because once it gets past the critical angle, at the critical angle it's all refracted along the surface. Beyond the critical angle, it cannot be refracted, it all gets reflected. And obviously, as we learnt in the last video, when you're talking about reflection, then the angle of incidence will equal the angle of reflection. The angle between the incident ray and the normal and the reflected ray and the normal will be the same. So in these circumstances, all the light that is hitting the surface is being reflected back into the water. None of it is being transmitted into the air, and that is called total internal reflection, because it is all totally internally reflected within the substance where the light originates. So can we calculate the critical angle for, say, water? So this is water, this is air, and remember you always have to go from more dense into less dense. The critical angle is the angle at which, this is now the angle of incidence, which equals the critical angle C, and that is the angle at which the refracted light goes along the surface of the water, which means that the angle of refraction is 90 degrees. 90 degrees to the normal. So now all we have to do is to apply Snell's law, which says that sine I divided by sine R is equal to 1 over n, remember, because we're going from more dense to less dense, so it's the 1 over n formula, and that means that sine I is going to be sine R divided by n. Sine I is the sine of the critical angle. Sine R is the sine of 90 degrees. The sine of 90 degrees is 1. So that means that the sine of the critical angle, which I'll call C, because that's the angle of incidence, which is the critical angle, is equal to 1 over n. We know that for water, N is 1.33. So that's 1 over 1.33. So now we know that what we've got to do is get the calculator out, work out what 1 over 1.33 is, and then find the arc sine of that value. And what you will find is that the critical angle is 48.75 degrees. So if you shine a light at an angle which is 48.75 degrees, then it will be refracted along the surface, assuming you're doing it in water. If you shine a light which is more than 48.75 degrees, then it will be totally internally reflected. What about glass? If you're going from glass to air, suppose this is now glass instead of water, you've still got exactly the same formula. You've got that sine I, which of course is sine C, divided by sine R, which is of course sine of 90 degrees, which is 1, is equal to 1 over N. So now we've got that sine C is equal to 1 over N because sine R is 1. And that for glass is 1 over 1.5 because the refractive index of glass is 1.5. And if you work that out, you'll find that the angle is equal to, of the order of, 42 degrees. Now the relevance of that is, let's just consider a piece of glass fibre. Right, so there's air outside the fibre, but the fibre itself is made of glass, so it's a thin glass fibre. And I shine a light whose angle is 45 degrees. So the angle of incidence is 45 degrees, which is greater than the critical angle. Consequently, that light will be totally internally reflected, and obviously the angle of reflection will be 45 degrees. At this side, it will strike the glass at 45 degrees, just by symmetry. That's more than the critical angle, so that too will be totally internally reflected at an angle of 45 degrees. That will hit this side at 45 degrees, so that will be totally internally reflected, and so it will go on, because the angle at which it hits the glass is always greater than the critical angle. So light passes down the glass without any of it emerging from the glass itself. It's all totally internally reflected. And the nature of this, which is called an optical fibre, is that even if you bend the fibre, you find that the light is still totally internally reflected. So you can use optical fibres to send light, but also you can encode signals in light. So one example of the way in which endoscopes are used, and I've had one of these myself, they're not quite as bad as they appear, is that if you have to go and have a doctor check up on your stomach, then what he will do is he will usually sedate you first, but not necessarily. He will pass a tube. It's a thin tube and it's effectively got a glass optical fibre in it. In fact, it's usually got two. Because it's bendy, it bends down past your throat and down and into your tummy, into your stomach. And those two glass optical fibres, one of them is sending light. So that in fact the contents of your stomach, or rather the lining of your stomach, can be seen. There's light inside your stomach. And the second optical fibre is the return journey. What you will find is right on the end of this there will be a very tiny camera. That camera will send signals back through the return optical fibre, and that will then be sent to a television monitor, so the doctor can actually see the contents, or more accurately the lining of your stomach, if he needs to check out if something's been going wrong. That's called endoscopy. The glass tube, which is very thin, is called an endoscope. It's a bit uncomfortable when they put it through down past your throat, but it's doing a good thing. It's using the principle of total internal reflection, first to send the light down the tube so that you can illuminate what you're looking at, and secondly to send encoded signals in this light back up the tube so that you can view the images on a television screen. You can use this principle of total internal reflection in glass by using what's called a glass prism instead of a mirror. Because glass can reflect, obviously, light. Let's suppose we have a piece of glass where these two angles are 45 degrees and this angle, of course, is a right angle. And let's suppose we send in light like this. We draw the normal, and what we find is that this angle, like this angle, is 45 degrees. 45 degrees is greater than the critical angle of glass, which you may remember was 42 degrees. So consequently, it is all totally internally reflected at an angle of 45 degrees, which means it now is coming entirely in the left-right direction, where it hits the glass at an angle of 45 degrees, which is greater than the critical angle, and so all of it will be totally internally reflected at an angle of 45 degrees. And as we've already shown, when it gets to the surface of the glass, it's getting to the surface at 90 degrees, so it just passes straight through. Both on this way in and on this way out, it passes straight across because the incident angle is naught, and therefore the refracted angle is naught, so they just go straight across. But it's at this point that you get total internal reflection and the light is reflected. So this is essentially doing the same thing that a mirror does. It simply sends the light back from whence it came. That was all special case number 2. This is special case number 3, and this says that the refractive index for a particular substance, such as glass, will vary dependent on the colour of the light that you pass through the material. So it's not as though the refractive index is a constant for all forms of light. Here is what's called a prism. It's just essentially a triangular piece of glass. And if you send in, let's say, red light, then here is the normal. Some of it will be reflected, we know, we're not worried about that. But some of it will be refracted. This is air, of course, on the outside. And it's glass in the middle. So if we're going from air to glass, we're going to be refracted towards the normal, something like that. Then when we hit the surface, we're now going to be refracted away from the normal, because we're going from glass to air. So the progress of red light through our prism looks something like that, nothing exceptional. We've looked at this before. Just to remind you that the angle of incidence, when we come in, will yield an angle of refraction which is smaller because we're moving towards the normal. Then at this point, the angle of incidence will produce a larger angle of refraction because we're going from a more dense to a less dense medium. And it looks something like that. But if you were instead to have chosen blue light, which I will use a pencil for, then in fact the refraction will be more towards the normal. So in fact the refraction will go like that, and then like that. So blue light is refracted more than red light. Consequently, the red light appears here, but the blue, or let's say violet light, appears here. And all the colours of the rainbow will have been split up similarly. So you will get the famous Richard of York gained battles in vain, which is just the way I remembered the colours of the rainbow: red, orange, yellow, green, blue, indigo, violet. So if you send plain white light, sunlight if you like, into your prism, because white light is made up of all the colours of the rainbow, once it gets in the prism, the different colours travel at different speeds in glass. That's why they have different refractive indexes. And so the colours are separated out as they progress through the prism, and they're more separated out as they emerge from the prism. And so you see white light going in, but if you look here, if your eye is here, what you will actually see is a rainbow, if you like, a spectrum of colours emerging from the prism. You'll recall that so far we've been saying that the refractive index of glass is 1.5, and that's a kind of a rough average, as you'll see. But in fact, the refractive index of glass for red light is 1.514, whereas the refractive index for glass for blue light is 1.523. So you can see that 1.5 is not bad as an average, but the refractive index of blue light is greater than the refractive index of red light in glass. We know that the refractive index is, by definition, the speed of light in air or in a vacuum divided by the speed of light in the material. So as the speed of light in the material increases, the refractive index decreases. So the lower the refractive index, the greater the speed in the material. So since red light has a lower refractive index than blue light, it means its speed in that material must be greater. So the speed of light of red light in glass is greater than the speed of light of blue light in glass. Of course, in air, they both travel at pretty much the same speed, 3 times 10 to the 8th meters per second. But red light in glass travels faster than blue light in glass. Consequently, because of this formula here, the refractive index of red light is less than the refractive index of blue light.